Welcome to the starting point of calculus. Limits formally are the point really where algebra turns into calculus, but the interesting or strange thing about limits is that when you are asking someone who is working with calculus, like an engineer or a scientist, they will tell you that calculus is about derivatives, they will tell you calculus is about integrals. They may not talk about limits very much, and if you ask them about limits, memory may well be rather hazy. And so the question becomes, why do we worry about limits so much when calculus is about derivatives and integrals? Well, it turns out that limits provide the formal foundation for derivatives and integrals, and so before we start doing all that algebra, which is important in and of its own right because it prepares us for calculations, before we do that, let's take a quick look as to how limits, at least pictorially, are the foundation for all the more well-known concepts of calculus. So we're starting with derivatives, and one of the standard motivations for calculus is the instantaneous velocity of an object. Now, the velocity of an object always is the quotient of distance over time. That's always v equals s over t, where s is the good German word Strecke. So it's not d over t, it's just standard notation. But the challenge there is that an object's velocity can change in time. So for a good measurement of the velocity, we would want this little time over which we measure the velocity, we would want that to be small. In fact, that's how a radar gun works. It computes the average velocity over a very short time interval, which is defined by that radar ping. Ideally, for the theoretical considerations that ultimately allow us to just lay the foundation for the various fascinating applications, we would want t to be 0. And that's one of those moments because, well, we can't divide by 0. But limits will allow us to shrink the denominator arbitrarily close to 0, and that will basically be the stand-in for division by 0, because no matter what kind of mathematics we do, denominators will never actually be 0. Okay, tangent lines are a similar story. A tangent line is a line, tangent line at a point is a line that just barely touches the graph at that point. So it should be something that just goes along with the cursor here. Well, the challenge of that is that algebra can't define what barely touches means. What you can define with algebra is lines that cut through the graph at two well-defined points, right? We've got one base point, we get another point, and then we just push the line through that. Now that's not a tangent line, but that's what is called a secant line. Now if we compute a secant line with a second point that is closer to our base point, or even closer, or closer, or closer, then we're beginning to see that even though those are still secants, they're starting to look like they are just barely touching the graph, which is what the tangent line is supposed to do. And so the tangent line, ultimately, you can see here the difference between these two is negligible in the picture. There's a little bit of a tilt, but these secant lines get very, very close to the tangent line, and well, again, the idea would be to push that second point all the way into the first point, and we can't do that because then we would have to divide by 0 when we compute that slope. So division by 0 is something that is not made possible by limits, but limits will be something that allows us to circumvent divisions by 0. And that is something that also occurs in graphs of rational functions, which you may have seen in earlier classes, where when we're looking at the graph of this function x squared plus 2x minus 3 over x minus 1, you sketch the graph on a graphing calculator. It looks like a straight line, and then of course your teacher will tell you, no, there's that hole in here because you can't divide by 0 at x equals 1. And that's what sometimes happens, and in fact, that's the kind of thing that we can conquer very nicely with limits. When you've got a division by 0 that cancels out, that's actually typically the best case scenario for when you're computing a limit. On the other hand, you could also have the x squared plus 2x minus 3 divided by x plus 1. And in that case, you've got a division by 0 at -1, and the function actually blows up at -1, right? It goes to plus infinity, it goes to minus infinity on the right. That is something that can also be investigated by limits. What happens when there is a singularity. And that is also important in the sciences and in engineering design, because singularities typically are something that you want to avoid. If you've got something that describes a design and that has a singularity, well, that's a place where the design is likely to break. And that's vertical tangent lines, and that's also, if we're looking at it graphically, this is something that you probably have seen before in an algebra class, and it was something that was a little bit mysterious. Well, limits will allow us to really take the mystery out of this step. Integration typically talks about areas under curves, and well, if you're looking at this parabola here, or actually no, that's not a parabola, that's the sine function, scaled so that here's 0, here's pi, here's 1, of course, on the y-axis. That's the sine function. If you're interested in the area under the sine function between 0 and pi, well, you could just replace that area with a rectangle and say that that's the area, but obviously that doesn't work out. Well, you could look for a formula, but that formula doesn't exist, at least not as a formula like the formula for the area of a circle or so. But what you can do is you can approximate that area with smaller and smaller and smaller rectangles. And you can see, as opposed to the first one that I had, these rectangles here, they're all rectangles. So we can compute that area just with base times height, and we just have to add up, of course, the area of these 8 things. But that area looks pretty close to what it should be. And again, in the limit, as you use more and more rectangles in the limit, you would use infinitely many rectangles, you get the actual area under that curve. So that's another thing that limits are good for. And that gets us to the point where we can talk about inputs that get large. For example, if you're looking at the graph of x over x plus 3, well, that thing seems to level out, and you get what is called a horizontal tangent line. Again, something that is sometimes talked about in algebra class, but without using limits and so on. Well, limits will tell us how to compute those kinds of horizontal tangents. Limits will also allow us to compute horizontal asymptotes. Sorry. Limits will also allow us to compute oblique asymptotes. If you've got something like x cubed minus 4x over x squared plus 1. Well, that thing looks like this, and it looks like it's straightening out into a line here. So it looks like it's getting really close to that line, and if we zoom out a little bit, like so, we see that, in fact, for large values of x, the asymptote is indistinguishable from the graph. And again, limits will allow us to compute those things and to take the mystery behind those things just out of the picture. And so, overall, as a summary, limits are important because, well, with limits we investigate what happens when a denominator becomes very small. And with limits we can also investigate what happens when an input parameter gets very large. And finally, well, limits are also important because they will reinforce a lot of the algebra that you've done as preparatory work up to this stage. And that is something that should not be knocked here. It's just algebra, it's just math, but we want to get it right. And the prep work that you're doing in computing a lot of rather ugly limits will give you the ability to do symbolic math at a more instinctive level. It will allow you to do computations without worrying about them too much, so that ultimately you can rightly say, yeah, this is just math, let me concentrate on what the concepts underneath is, I can do the computations. And that can go very far. In my differential equations videos, which you may watch after you've done calculus maybe, which you might watch, at that time I've been apparently really pushing that point, and I recently got an email back from a student who said, well, you've pushed that over and over again, and recently somebody asks me something about physical chemistry. Now this student is a gentleman who doesn't like chemistry at all, who just took the required chemistry and wanted to get away from it. He wants to be an electrical engineer. But he thought, well, let's just humor this friend of mine and see if I can explain some physical chemistry. And he realized it's just math. And as soon as he got over the mathematics, yeah, he still had to deal with the chemistry aspect of it, but he was able to explain that stuff, and he was very happy about it, sent me a very nice email that I definitely cherish. And the reason why I'm telling you this is because, well, there will be quite a few computations in here, and they may well be frustrating, they may well be ugly, they may well be boring, but it's just math. It's something that we just have to be able to do. The underlying ideas are the stuff that we've got in this presentation. And what we get out of it is, if computation is just something that we do, we can really focus on the stuff that is cool about this. So I'll see you in the next presentation. Let's get to it.